Okay, so we want to use divergence theorem to integrate the surface area of this thing over the region bounded by this paraboloid, this cylinder, and this plane, right? So first, we kind of want to get a feel for what these surfaces are. Okay, well, the paraboloid, for given y, you have x squared plus z squared equals y plus 2, right? So the paraboloid could also be written x squared plus z squared equals y plus 2. And of course, y has to be then greater than negative 2. This isn't given, but you see this immediately because the sum of two squares is positive, or is it at least 0. So y plus 2 has to be at least 0, means y has to be greater than or equal to negative 2, right? Cross sections. Are circles. Cross sections for y equals constant are circles of radius square root of y plus 2. Okay? And then you do cross sections with x or z. Cross section for x equals 0 looks like what? You got y and you've got z. And y can be, okay, in the yz plane, that would be the point negative 2, 0. And then when y equals negative 1, you're going to get like 1 here and negative 1 here. When y equals 2, then you're going to have radius square root of 4. So it's going to, y is 2, you come up with square root of negative 4, and you can, just kind of sketch what that looks like. Okay, these being now units of the y-axis and units of the z-axis. Okay? And it's just a solid of revolution. You just revolve this surface because, of course, in the xz plane it looks identical. And besides, the cross sections are circles, so this is just a solid of revolution. Just rotate that parabola. Okay? Now, let's look at the cylinder and the plane and then see how they cut. Okay? So now we see that if x is this way, y is this way, and z is this way, we have a paraboloid, just a solid of revolution around the y-axis. Okay, this thing. Okay, well, now in the cylinder, well, that's in 3 dimensions. It's easy to draw that. Here's x, here's y, and here's z. Then x squared plus z squared equals 1 in the xz plane is just a circle of radius 1. Unit circle, right? And it's the same in any y equals constant plane, right? Any plane parallel to the xz plane, you're still going to have that circle, right? So it's just an infinite cylinder. Looks like this, and now the back of this thing's maybe hidden. Okay? Basically, it's just a tube. And it surrounds the y-axis. Okay? Now how does that articulate with the parabola?
It gives a rounded base to it.
It's going to cut it here, because this is just a solid of revolution of the y equals 1, or the z equals 1. Okay, in the YZ plane, it's just a z equals 1 line cut like this, okay? So now you know that you have this part of the paraboloid, but then it's cut by this straight line. So it's just a long tube with a blunt end. Make sense? So just visualizing, okay? Then you got to cut it with the plane x plus y equals 2, okay? So, well, you can see that if you draw this in 3 dimensions, we can actually do a fairly decent job, at least, of sketching the thing. It's like this, with a blunt end, and it ends at the point -2 or 0, -2, 0, right? So here we have the point 0, -2, 0. In a tube of radius 1, y-axis being its central axis, its axis of symmetry. Okay? Now, symmetry gets all screwed up when you now cut it with the plane x plus y equals 2. What's the plane x plus y equals 2?
A vertical plane that intersects at 2, 0, 0 and 0, 2, 0? Or those are two of its points.
0, 2, 0 and 2, 0, 0, is that what you said?
I think so.
Yeah, we'll go through those points. Okay? So basically, we're x equals 2. Now remember, this is of radius 1, so it's like when this crosses the x-axis, it's at x equals 1, and it's not very well drawn, but like here's x equals 2, right? So here's the point 2, 0, 0. And on the y, here's the point 0, 2, 0. Okay? And now you've got a vertical plane. Above and below, and it cuts this cylinder, right? So you just got this long tube, and it's only the tube part that's getting cut by this thing. The blunt end here is on the negative part of the y-axis, right? It's to the left of the xz plane, and this thing doesn't cut it at all to the left of the xz plane, right? So now if you look at this thing from above, which is a place where the plane would just appear to be a line, right? So we cut this thing from above. Be nice if I draw a straight line. Okay, so we got this tube, it's circular up to here and blunt on this end, right? And now, here's y, and here's x, just to kind of orient it the way you would see it if you looked up here, right? If you want to rotate it this way, that's fine, okay? And we've got the plane that cuts this thing at 2 here and at 2 here, so it's a line like so. So now what we're looking at is this surface, which is just, again, a long circular tube sliced right here. You can visualize that, okay? Hand me your thermos, let me just slice it. No.
It's kind of like a whistle in how it looks.
The what?
Kind of like a whistle, except a whistle that is rounded perfectly instead of just being flat on.
Yeah, yeah. If it was a whistle, you'd have, you know, you'd rotate it so that the plane is up like this, and, you know, blow the whistle. Make sense? Okay. So, again, and then it gets blunt here. Okay. So that's what the thing looks like. Now, we don't want to do a surface integral. Because to do that, we'd have to parameterize this thing, and we'd have to break it into at least 2 sections. and probably 3. One for the blunt end, one for the cylindrical section, and then one for the truncated section, okay?
How is the volume integral any better?
I'm sorry?
How is a volume integral any better?
Oh, we're going to see. That's what we're going to do. I'm going to do the volume integral. I'll let you do the surface integral. Okay? Well, let's see. We got a little time. Okay. Except I don't want to risk having to split this video, so I'm going to stop.